Hi, we are going to be talking about chemical bonding. Chemical bonding is a very important topic, and many students think it's easy, so you don't have to pay much attention. It will become very, very important later on in the semester. Okay, so you want to get it right today. Besides, chemistry is all about bonds. In chemical reactions, you don't create or destroy atoms, you just rearrange them. Kind of like playing with Legos. So when you break down a molecule, you break down the old bonds, you make a new molecule, you form new bonds. It's all about bonds. In a chemical reaction, the nucleus does not change. That means the number of protons remains constant, the atomic number remains constant, so the element does not change. But electrons is a different thing. And we're talking here about valence electrons, okay? Valence electrons are going to participate in the chemical reaction, forming new bonds. So they can be gained, they can be lost, they can be shared, and please don't misunderstand it. This is not a random process. The atom does not pick up a card that says lose 2 electrons, okay? There is a principle behind it that we call the octet rule, saying that the atoms want to achieve a full outer shell. For most atoms you're going to be dealing with, that means 8 valence electrons. That's where the name octet comes from. Yes, there are bigger atoms. We're not going to worry about them for now. You have hydrogen that all it can hold is 2 electrons in the only shell it has. But most of the atoms you're going to be dealing with are satisfied if they have 8 electrons in the outermost shell. So we said when electrons are transferred, ions form. Why? Because one atom is giving up electrons, so it becomes a positive ion. Another one is picking up electrons, becomes negative, so you form ions, some positive, some negative, and the electrostatic attraction between them forms the ionic bond. When electrons instead are shared, you have a covalent bond. And this allows us to classify compounds as being ionic or molecular, depending whether they have mostly ionic bonds or covalent bonds. That's going to affect many of their properties. So once again, bonds are very, very important. So let's begin with ionic bonds. We said that one atom is going to lose electrons. Remember, the number of protons does not change. So if it has less electrons, that means it has more protons than electrons. So you form a positive ion that we call a cation. And I had one student once write on the exam, cats are positively great. A nice way to remember that cations are positive, right? When the atom gains electrons, and again assuming the number of protons does not change, then it has more electrons, more negative charges than positive, so you form a negative ion that we call an anion. And once again, the attraction between the two of them forms the ionic bond. Examples, sodium chloride, most typical ionic compound I can think of. Sodium has 11 electrons. So in the first level, you can put 2. In the second, you can put 8, 2, 3, 4, 5, 6, and 8. Now there's only 1 electron left. Sodium could try, in theory, to fill the third layer or empty it because the layer underneath is already full. Okay? So it can lose 1 electron or it can gain 7 electrons. It's very obvious that it's easier to lose 1 than try to gain 7. So sodium only has 2 layers now, but we said that the second one was already full, 4, 5, 6, 7, 8. The outermost layer is full, sodium is happy, but it lost 1 electron, so it becomes a sodium plus 1 ion. If you look at chlorine, it has 17 electrons. You can look it up in the periodic table. Okay? So you have 2. Now we have 8. 2, 3, 4, 5, 6, 7, 8. Now you have 7. 1, 2, 4, 5, 6, 7. Just like sodium, it has 2 choices. It can fill the third shell, which means gain 1 electron, or it can get rid of these electrons because the second layer is already full, lose 7 electrons. Once again, 1 is equal to 7, so it will gain 1 electron, and our chlorine has 2 electrons, 8 here, 2, 3, 4, 5, 6, 7, 8, and now it has 8 electrons in the outermost shell. Again, chlorine has a full outermost shell, but because it gained 1 electron, it's minus 1 ion. And the attraction between the sodium ion and the chlorine ion, that's the ionic bond. Okay? Can you predict ion charges? For most examples, yes. Main group metals, those are the elements to the left of the periodic table. You know the group tells you the number of valence electrons. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 3 valence electrons. Notice that we skip transition metals, but we'll get to them. So obviously it's very easy to lose 1, 2, 3 electrons and end up with plus 1, plus 2, plus 3 ions. Many non-metals, they're very close to filling the outermost shell or to have the same number of electrons that a noble gas. So if you go to group 17, they have 7 electrons. Group 16 has 6, group 15 has 5. So they're going to gain 1, 2, 3, and they form minus 1, minus 2, minus 3 ions. You can predict this one just by looking at the periodic table to see in which group the atom is located. An example of that is calcium. You look in the periodic table, it's in group 2, has 20 protons and 20 electrons. Because it's in group 2, we know there is 2 valence electrons, or 2 electrons in the outermost shell. So it loses those 2 electrons and becomes calcium plus 2. That's what we have predicted, because it was in group 2 that formed an ion with a plus 2 charge. We skip transition metals because they and a few, the transition metals and some of the main group metals, they're going to form sometimes 2 or even more ions. The reason is they have d orbitals, and without making this a very long lecture, it turns them into 2-year-olds. They know what they're supposed to do, they don't care, they do whatever they want. You see this in chemistry all the time. We are going to blame these d orbitals for a bunch of different things. In this case, these atoms can lose electrons from an s orbital or from a d orbital, and they can choose, and you cannot predict which one. So basically, they form more than one ion. Now, what if you have, 2 people with the same first name? How do you tell them apart? By using a last name. So these ions, and only these ions, are going to have a last name. That's the charge of the ion, written as a Roman numeral in parentheses after the name of the metal. So iron plus 2 is called as iron 2. Iron plus 3 is iron 3. Please keep in mind, this is only for atoms that form more than one ion. I had the students writing an exam, magnesium 2. And they get very upset when I come and say, wrong. What do you mean it's wrong? The ion was magnesium plus 2. So it's magnesium 2? No. Because if you look at magnesium, it's in group 2. It can only form one ion, so you do not put a Roman numeral. That's not my rule. That's not your book's rule. That comes from the UPAC, the International Union for Pure and Applied Chemistry, and everybody in chemistry follows the UPAC rules. Okay? So here you have a list of charges, and before you freak out, you can predict most of them. We say you can predict group 1, group 2, group 13, group 15, 16, and 17. So whatever's left in here, these are the ones that are going to give you a hard time because they have d orbitals, and these ones you just need to memorize them. Okay? I try to cut down memory work in chemistry as much as possible, but some things you just need to memorize. This you need to know. Covalent bonds happen when 2 atoms decide to share. Basically, both have similar tendency to attract electrons, Nobody wants to give up an electron. So sharing is the only alternative. Let me give you an example. Hydrogen gas is H2. It's formed of two hydrogen atoms. Each one has one valence electron. So you have a hydrogen with one valence electron, another hydrogen. Can you imagine the first hydrogen coming and saying, hey, give me the electron so I can fill my outermost shell? And this hydrogen derives says, you crazy what? I need one electron. Nobody's going to give up an electron because they both need one. So basically what they do is they say, let's share them. These electrons are going to be considered belonging to both of them. Each one actually orbits around both of the nuclei. So now both hydrogens have two electrons in the outermost shell. They're happy and they form a covalent bond. This works real good when you have identical atoms, like the example I just gave you, because they both have the same attraction for the electrons. So the electrons are shared equally, and we call that pure covalent bond. But what about when the atoms are different? Most of the time, that means that one of them is going to have a stronger attraction. Okay? So that's going to polarize the electron density, shift electron density. So this unequal distribution of electrons, we know it as a polar covalent bond. Basically, instead of every electron spending 50% of the time over one atom and then 50% over the other one, they're going to divide unequally. Maybe it's 70-30, maybe it's 60-40. Depends on the difference in the strength between the two atoms. But the point is, it's not an equal distribution, so that's a polar covalent bond. The atom that's stronger is going to attract the electrons closer. So it develops a partial negative charge. Chlorine has much stronger attraction for the electrons than hydrogen, so this bond is delocalized and you get a partial negative charge of the chlorine. Hydrogen doesn't have the electron all the time it was supposed to, so it gets a partial positive charge. Let me make it very clear, these charges are very small, they're less than one charge, okay? But they're extremely important in chemistry.